All right, and we're off to single displacement reactions. In some textbooks, this is called single replacement. I like single displacement better. Basically, what happens is you have element 1 plus compound 1, and they will react to produce element 2, which came out of compound 1, and compound 2, which is a mixture of compound 1 and element 1. So basically, what happens is we've got two general reactions here. We have metal A as an element, and it reacts with compound BC. A, if it can, will bump out or displace element B in the compound. And as a result, you will get element B by itself, and A is now a cation, a positive ion, in the new compound. If you have a halogen as the element, so remember it's a diatomic element, so there's two of them. If this element reacts with this compound, it will bump out the like element in the compound. So it will bump out the halogen in the compound. So you will get a new compound, and the other halogen is as an element. And it does not matter if you have AZ plus Y2 or Y2 plus AZ. The order of the products, just like 2 plus 1 is equal to 1 plus 2, it doesn't matter which order you put the two products in. At the moment, neither one of these two general reactions are balanced. This is just a general representation of what is happening. So if your element is a metal, and if your element is a halogen. So we're going to look at two different ways to decide whether or not the reaction goes, whether or not the element can actually bump out the other element in the compound. And we're going to look at using an activity series and using our electronegativity values from the periodic table. So first we're going to look at using an activity series. So an activity series is basically a reactivity series. It's a list of elements in order of reactivity from highest to lowest. There are two reactivity series. There's one with metals, and then there's one with halogens. And what you do is you look at the element on the reactant side that's all by itself, and that will tell you which one of the series you're going to use. So here's an example of an activity series, and you can see that we have metals in this column and halogens in the second column. So you look at the element on the left-hand side of the arrow, on the reactant side, identify what type of an element it is, and that will determine which column you use. So basically, if the element, the A or the Z, in the reaction is higher than the similar element inside the compound, then the reaction goes, and you get new products. If it's not higher, then the reaction will not proceed, and we say it's an NR, a no reaction. So let's take a look at this activity series. So if you are higher up here and the other element is down here, you can bump that element in the compound out. If the element that's all by itself is lower than the element inside the compound, we're going to have no reaction. So we're going to do a couple of examples using this. Just put this to the side. Okay, so lithium to sodium. So lithium to sodium. Well, let's use highlighter. Lithium to sodium. These elements can displace hydrogen if it's in an acid or in water. Below sodium, those metals, so from magnesium to lead, these metals can only displace hydrogen if it's reacting with an acid. So the yellow highlighted ones can react or bump out hydrogen in water or an acid, and magnesium to lead will bump out only hydrogen in an acid formula. Oops. Okay. So let's do a couple of examples using metals. So first one, aluminum plus silver nitrate. Oh, that's a typo. AgNO3. So silver nitrate. Okay, so aluminum plus silver nitrate. The aluminum is the element, and the silver in the compound is the similar element. So for the metals, you will always be looking at the element at the beginning of the formula for the compound. So aluminum. So find aluminum on the chart. And is it higher than silver? So aluminum is here, and silver is down here. So aluminum is higher than silver, so it is more reactive, so it will bump out silver. So you will end up with silver as a solid because it's in the elemental form. Mercury is the only liquid element, metal. And then we have to write the formula for aluminum nitrate. Aluminum has a charge of +3. Nitrate is 1-, so we need 3 of them. So now you can go ahead and balance. We have 3 nitrates on the right, so we need 3 on the left, which changes our amount of silver. So now we need 3 silvers. So we have 1 aluminum, 3 silvers, 3 NO3s, 3 NO3s. Balanced. And that is AQ. All right, next one that's a metal example. Copper plus zinc nitrate. So find copper. And zinc. Here's copper. Here's copper. And here's zinc. So zinc is actually higher. So because the element is lower than the element in the compound, this reaction will not proceed. this reaction will not occur. So because copper is lower, it's less reactive. So this will be an NR, no reaction. So if we had zinc metal and we placed it in copper 2 nitrate, we would get a reaction, because then the zinc would be higher than the copper in the compound. So the reverse, the copper plus the zinc nitrate, is not reactive. No reaction. All right, let's do one more with a metal. So calcium plus water. So calcium is up here. Hydrogen is down here. And calcium is just above sodium, so it does bump hydrogen out from water. So what happens when you have a metal plus water? You will make the metal hydroxide. And hydrogen gas. So always, if you have a single displacement reaction, you will form the metallic hydroxide, so a base, plus hydrogen gas. Now all we have to do is balance this equation. So we have one calcium, two oxygens, but we have one oxygen over here. So the rule for an even and an odd is double the odd. Water's odd, so I'm going to double it. So now we have two oxygens on both sides. 2 times 1 and 2 times 1. That gives me 4 hydrogens. I've got 2 hydrogens here and 2 hydrogens here for a total of 4. So this is now balanced. The next reaction has to do with halogens, so we're going to use the second column. So we're going to look at the halogens. So if the element that's all by itself is higher than the halogen that's in the compound, then you will have a reaction. If it's lower, you will have an NR, a no reaction. So we've got chlorine as the element and fluorine in the compound. Fluorine is more reactive than chlorine. It's higher. So chlorine cannot bump fluorine out. So this is an NR, no reaction. Fluorine plus calcium chloride. Fluorine is higher than chlorine, so there will be a reaction. Fluorine will bump chlorine out, and we will make calcium fluoride and chlorine gas. And that is balanced. So there are many activity series online. I found this one on the website mentioned on just a couple of minutes ago. It's in blue. The other method that works is using the electronegativity rules, because sometimes you don't have an activity series, but you have access to electronegativity values. So there's two different rules, one for metals and one for halogens. So metals want to lose electrons. And if you're inside of a compound, an ionic compound, you have lost your electrons because you're a positive ion. So what happens is the one with the lowest electronegativity value will end up being in the compound, because that means it's lost its electrons. So for metals, the rule is find the electronegativity values for the two metals, or the metal plus the hydrogen, and compare them. The one with the lowest value will end up in the compound. Okay, so what I do is I write above the element the values for the electronegativity. So aluminum has electronegativity value of 1.5. Silver has an electronegativity value of 1.9. The lowest electronegativity value is 1.5. That element wants to be in the compound with nitrate. Therefore, there will be a reaction because it's not. So aluminum will displace silver. We will form aluminum nitrate, and we will displace silver. All right, lead and zinc. Lead has an electronegativity value of 1.8. Zinc has an electronegativity value of 1.6. So then I circle the one with the lowest value. That lowest value is in a compound already, so this will be a no reaction, because the element, the metal with the lowest electronegativity, is already in the compound. So that's an NR. Sodium. Sodium is 0.9. Hydrogen is 2.1. So again, definitely have a reaction here, metal plus water. The lowest electronegativity wants to be in the compound, so we will form, same thing's going to happen, we're going to form a hydroxide as a compound, and we're going to make hydrogen gas as a product. So if you have a reaction of a metal plus water in a single displacement reaction, you will form the metallic hydroxide and hydrogen gas. All right, so we have to balance this. Sodium, there's one of each on both sides. There's one oxygen on both sides, so that's good news. But then there's 3 hydrogens, and there's 2 hydrogens on the left. So we've got our even on the left and our odd on the right. So again, we have to double something, and you double whichever species or entity that gave you the odd number. So we're going to double this one, because that's where our odd number of hydrogens showed up. So we now have 2 hydrogens here. We have 2 hydrogens here for a total of 4. So we have to multiply water, by 2 to make 4. that has changed our number of oxygens. So we now have 2 oxygens on the left, but we also now have 2 oxygens on the right. But we have 2 sodiums now on the right, so we also need to have 2 sodiums on the left. So now we've got an equal number of each element on both sides of the equation. All right, aluminum plus hydrochloric acid. Aluminum has an electronegativity value of 1.5, and hydrochloric acid, hydrochloric acid is 2.1. So the smaller of the two electronegativities wants to be in the compound. So aluminum will displace hydrogen from the compound. So we will make aluminum chloride, and the element hydrogen is written as H2. So now we have to balance. We need 3 chlorines. So we would have to multiply that by 3, but that would give us an odd number of hydrogens. And we have an even number of hydrogens on this side. So instead of multiplying this by 3, double that. So it's 6. So now we have 6 chlorines on the left. So we will have to multiply aluminum chloride by 2, which gives us 2 aluminums. So we have to multiply aluminum by 2. And then we have a total of 6 hydrogens, so we need 3 hydrogens to give us 6 atoms of hydrogen. And there you go. You just use electronegativities to predict whether a single displacement reaction occurs for metals. Okay, for the halogens. Because the halogens want to gain electrons, they want to become negative ions, we're going to be looking at the halogen with the highest electronegativity value. And that one will be the one that ends up in the compound. So we're going to have to get our electronegativity values again. So we're going to look at bromine. So bromine's electronegativity value is 2.8. Iodine is 2.5. This time I circle the highest value because we're doing halogens. That highest value wants to be in the compound. So because the highest value is currently with the element and not in the compound, so it's with the element, this reaction will go, the bromine will bump out the iodine. So our products will be sodium bromide plus iodine. So now we just have to balance. There's 2 bromines on the left, so we need 2 bromines on the right. We need 2 iodines on the left and 2 sodiums on the left. So we put a 2 out front there as well. Now that's balanced. All right, let's look at the second example. Chlorine plus magnesium fluoride. So chlorine has an electronegativity value of 3. Fluorine has an electronegativity value of 4. So we're only comparing the two halogens. The highest halogen is already in the compound, part of magnesium fluoride, so nothing's going to change for this reaction. It's already where it wants to be. So this is an NR and no reaction. Let's compare chlorine and iodine. So iodine is 2.5 and chlorine is 3.0. Highest electronegativity value is with the element outside of the compound. It wants to go in. So it will displace the halogen that's already there. So we will make iron, that's iron 3, chloride, plus iodine, the element. So now we just have to balance. We have 3 iodines here, 2 here. So it's a case of our even, uneven. So double the unevens, that gives us 6 iodines total. So we need a 3 over here because 3 times 2 is 6. And we will now need 2 FeCl3s because we need to balance the iron. So we have 2 Fe's. And that means our chlorine has changed too. Now we have 6 chlorines. And we need a 3 there. So there's a cascading effect once you start balancing. Often, one change you make will affect another element. So that is balancing single displacement reactions. Using 2 different methods, either using a reactivity series or electronegativity values.